Welcome again in the physics class. In today's topic we will take up that electromagnetic induction EMI, the last part. Okay, in the previous video we have discussed about the magnetic flux, Faraday's experiments, Faraday's laws of electromagnetic induction, and Lenz's law and law of conservation of energy. In today's video we will discuss about expression for induced EMF based on the laws of electromagnetic induction, what we call as Faraday's laws of electromagnetic induction. Next, method of producing induced EMF by changing magnetic field, by changing the area of the coil in motional EMF, by changing the relative orientation of the coil with the magnetic field, Eeddy currents, self-induction and self-inductance, mutual induction and mutual inductance, and lastly we will try to give you some additional information related with electromagnetic induction.
Now let's try to find out the expression of the induced EMF as per your second law of what your Faraday's laws of electromagnetic induction. E is equal to what? Minus d phi by dt. Minus is given by your Lenz's law. Okay, this will give you the direction of the induced EMF. Otherwise, if you take it only the magnitude, then E will be equal to d phi by dt. So d phi means change in flux, so phi 2 minus phi 1 by t, right? And if you are taking this is only for one turn, if there are capital N total number of turns in the coil, then you need to multiply it by capital N in it. Got it? Same is the case in the case of current also. Current means what? V times V divided by R, or what? Potential difference divided by R by your Ohm's law. So E by R will be equal to what? I. So your current for a single turn will be what? Minus d phi divided by R dt. You just multiply by R here, then you will get I by R here, d phi by R dt. That is what? If you are having for that of charge, this is for single turn of the what? Circuit or solenoid, then there is no factor of capital N here. But if you take it for the whole solenoid, then you need to multiply by the total number of turn capital N as it is here. Okay, and if you want to express it for charge, we know that your charge, rate of flow of charge is equal to current, right? So I will be equal to d phi by dt. So your d phi, dq by dt, rate of change of rate of flow of charge, we call it as current. So dq by dt is equal to what? I. So your dq can be written as, if you cross multiply it on that side, then dt will cancel and it will be what? D phi by R. So your minus d phi by R will give you the small amount of charge that is flowing through the solenoid due to the what? Induced EMF. Now you will see that induced EMF is independent of resistance R. Here there is no factor capital R, is not it? But here it is a factor R is there. Induced EMF does not depend on the resistance of the circuit, whereas your induced current and the induced charge depends on the resistance R. In both expression, R is involved here, right? Now method of producing this induced EMF. Now you know that your phi is equal to what? B dot A vector, right? V vector dot A vector, or you can express this as B A cosine of theta. So your magnetic, okay, field induction can be changed, area can be changed, orientation can be changed, or combination of these three can be changed so as to produce change in magnetic flux. So your induced EMF depends upon this change in this magnetic flux. Okay, and again it is change in B, change in A, change in theta. So your induced EMF will surely depend on to these three individually B, A and theta, where B is the magnetic field induction, or rather the strength, and area is the area of the coil or the surface of the coil or the circuit, you can say, or conductor, and this is the angle between the area vector and the magnetic field vector, and in these three individually or collectively onto these three parameters. So we say that by changing the magnetic field, by changing individually this magnetic field, you can have or you can produce induced EMF. So magnetic flux phi can be changed by changing the magnetic field B, and hence EMF can be induced in the circuit as done in the Faraday's experiment, right? Now let's see in the next case, by changing the area, capital A. Okay, if area of the circuit or the coil changes, then what happens? You will have the change in the magnetic flux. So what happens? There will be production or generation of induced EMF in the circuit. Next is what it will be in the case of orientation. But first let's try to see about this explanation of this, by changing the area of the coil in the magnetic field. So magnetic field, in this case we have taken that magnetic field is directing inward perpendicular to the plane of the screen, and it is getting inward, okay, magnetic field direction I mean. Now a rectangular current loop or conductor is there. Say suppose PQRS is the rectangular conductor, and if this rectangular conductor is brought or moved inside the magnetic field, okay, inside the when the this rectangular conductor is placed like this, still magnetic line of force is striking onto this conductor some part, but as there is no change in the magnetic flux linked with it, there will not be no induced EMF. But what happens when this rectangular coil is brought with some velocity v toward this direction, that means more and more toward the magnetic field, then what happens? The magnetic line of force, okay, in linking or striking or cutting to this area increases. Whenever 1, 2, 3, 4 is only there, when it is brought at this position, then this number of magnetic line of force increases, okay. So there is change in the magnetic line of force striking in it, perpendicular to it, I mean in a unit area, that is change. So if there is change in the magnetic flux, naturally there will be an induced EMF. Got it? Yes, let's see the loop. Okay, PQRS is slided into the uniform and perpendicular magnetic field like this, in this with a motion, in this motion with a velocity v. The change in the area of the coil under the influence of the magnetic field is dA. Let's take it that this is the area. That means area, this is not the area of the rectangle, rather this is the area of the coil through which there is change in the magnetic field linked with the coil, okay, not the area, rather this will be the area where there is magnetic field lines passing through it. So that area where the magnetic field, okay, lines passing through it normally is changed, and that area it is denoted by dA. Got it? So during that time, if it is B, that means B will be equal to what, your dL. If you take this as a V, then V will be equal to what, dL by dt, right? Got it? So your dL by dt, this is the distance that is moved. So if you know that length, then if you want to find out this L, then your L or length through which the magnetic line of force is crossing that area, it can be obtained by V dt, right? That length, this length is given by what, V dt here. Got it? So that can be obtained if you know the speed and the time, then the length that is what having or inside the magnetic field will be given by what, V into dt. Now this is that one. Let me remove it, that writing. clear all. Now yes, like this. So your d phi, that means this is the change in the magnetic flux, will be equal to b dot a. B is uniform, so there is no change in the magnetic flux, okay, a magnetic field induction, but there is a increase in the area of the coil where the magnetic line of force strike or link. Okay, so that dA will be equal to what? Area. So this is a rectangle, the shape of rectangle, so your dA change in area will be equal to what? Length into what? Breadth. If you take it this as length L, breadth as B dt, then that one length into what? Breadth will give you the area, okay, dA. So your E will be equal to minus d phi by dt, which is given by your what? Faraday's second law, and it will be equal to what? Your induced EMF will be equal to what? Minus BLV. So this E is equal to minus BLV. Sometimes it is also known as motional induced EMF. Why? Because it is due to the motion of this conductor inside the magnetic field. So when this conductor, if it is moved inside the magnetic field, and if there is change in the what? Area of the coil or conductor inside the magnetic field, due to this change in area, if induced EMF is developed, then that induced EMF developed due to the change in the area of this coil, we call it as what? Motional EMF. Due to the motion of the rectangular coil, it means, okay, it will be equal to minus BLV, right? The induced EMF is due to the motion of the loop, and so it is called as motional EMF. If the loop is pulled out, the magnetic field what? Induction. Okay, if this rectangular coil is moved away, then what happened? The induced EMF developed into that what? Coil will be what? Minus of this, minus of minus BLV. That means it will be plus BLV, right? That is what it is written here. So the direction of the induced current is anticlockwise in the loop, that is P prime, S prime, R prime, Q prime, okay, by Fleming right hand rule or Lenz's law. That means what? Here the direction of the current will be in this direction. Got it? P prime, S prime, R prime, Q prime, P prime, like that, in this direction, I mean. Got it? It will be in the anti-clockwise direction. So it is given by your Fleming's what? Right hand rule. The direction of the current okay, it is in this loop direction, so the magnetic field will be against that position, so it will be what? In this direction. Got it? Yes. Next, let's see. According to the Lenz's law, the direction of the induced current is such that it opposes the course of the magnetic flux. The course of the magnetic flux in that case was the motion of that rectangular loop to inside the magnetic field. So the direction of the magnetic field will be just opposite the direction of the induced EMF developed there. The direction of the induced EMF, okay, due to this current, induced EMF will be developed by this current. What is this current? This current is the induced current. So with this induced current, the magnetic flux, I mean the magnetic field direction or magnetic field induction, or you can also call it as magnetic field density. Okay, the direction of that magnetic field density be produced by this induced EMF will be outward, perpendicular to the plane of this screen, and it will be going outward, which will be against the direction of this induced EMF, I mean the magnetic field which is there. Okay, so this motion will try to oppose, okay, by that induced EMF. Got it? Yes. According to the Lenz's law, I have just read out this one. Here the cause of changing of magnetic flux is due to the motion of the loop and increase in the area of the coil in the neighboring magnetic field. Therefore, this motion of the loop is to be opposed as per Lenz's law. So the current is setting itself such that by Fleming's 11 rule, the conductor arm PS experience force to the right, whereas the loop is trying to move to the left. Okay, against this force, mechanical work is done, which is converted into electrical energy. Got it? There also we see what the lens law there. Okay, not if the loop is completely inside the boundary of the magnetic field, then if there is no motion of the rectangular loop, there is no change in the area where the magnetic field or magnetic flux is what not changed. In that case, there will not be no induced EMF in the current in the loop. Whenever there is a change in the motion of this what position of the rectangular loop, then only there is change in the what change in the small area. That area is what linked by the magnetic field. Okay, and if there is no change in the magnetic field area, then there will not be no induced EMF. So what when the rectangular loop is well within the magnetic field, there is no change in the area, so there will not be no induced EMF. Fleming right hand rule, this one we already have known and also learned in your class 10. Your thumb of the right hand, when you stretch it, your middle finger, thumb and index finger mutually perpendicular to each other, then your index finger will represent magnetic field, middle finger will represent current, and the direction of the force experienced by the conductor will be represented by your thumb. Okay, this is known as what your Fleming's right hand rule. By changing the orientation of the magnetic field, so your induced EMF can also be developed by changing this theta. If you change that theta, then what happened? Cosine of theta will be also changed. So what your magnetic flux phi will be changed. Phi is equal to B dot A vector, right? B vector dot A vector. So it will be equal to what? BA cosine of theta. So if that theta changes, naturally your magnetic flux will also change. If magnetic flux change is there, then induced EMF will be developed. So by changing this area of the coil, okay, by changing this orientation of the coil, okay, here if you change this theta, then what happen? It will surely change in the flux. If there is change in flux, then induced EMF will be also what produced. That is what this one you have learned in your electrostatics also. In that case it was electric field, here it is magnetic field. So what happened? Your phi will be equal to what? B dot A vector for one turn. If there are total number of turns capital N, then you need to multiply it by it. Now if this loop, rectangular loop, is rotating, okay, about its own axis, okay, with its angular velocity omega, then your theta, okay, theta is what? Angle between B vector and A vector. A vector is nothing, it is denoted by n cap here. This is the area vector of this rectangular loop. Okay, it will be always perpendicular to the plane of the area, rectangular area. So your n cap is nothing but it is your A vector. Your A vector and B vector, the angle between them is theta. So what happened? Your theta can be expressed as omega t, where omega is nothing but this is the angular velocity of the rotating rectangular coil. So your phi will be equal to what? NBA cosine of theta. So it will be omega t, where theta is omega t, as I said. Got it? So differentiating this, you will get that rate of change of magnetic flux, right? So differentiated this and BA, these are all constant. So you take it outside that differentiation, and if you differentiated this cosine of omega t, then it will be what? Minus sine omega t times of omega. One minus is there. Got it? So differentiation of cosine of theta will be what? Minus sine omega t. And if you differentiated this what omega t, you will get another omega. So your differentiation of this above equation phi is equal to NBA cosine of omega t will be equal to what? Minus NBA omega sine of omega t. So your E, by your Faraday's second law, E will be equal to minus d phi by dt. So if your d phi by dt is minus of this, then minus minus will be plus, and it will be what? NBA omega sine of omega t, this one. So your E will be equal to what? E naught sine of omega t. Why? Because this is equivalent to E naught. Got it? Right? When is happening this value, maximum value, sine of any angle will have the maximum value as +1. So +1, this one, when it is happening, when sine of this omega t is equal to 0. When omega t is equal to 0 means what? When this theta is equal to 0. When theta is equal to 0 means what? The area vector and b vector are parallel to each other. That means when theta is equal to 0 degree, a vector, area vector, capital A vector and magnetic field B vector, they are parallel to each other. Or you can also say that the plane of the rectangular coil is perpendicular to the magnetic field. In that case, maximum what induced EMF will be developed. Okay, as it keeps on rotating, what happen? It will be just like changing of that direction of the induced EMF, and not only direction changing periodically, rather it also continuously changing its magnitude. So this will be the expression of induced AC EMF. Okay, alternating AC means alternating EMF. The EMF changes continuously in magnitude and periodically it changes its direction. Okay, that is what it represents by this. So what happened at every time, what happened, the direction of the induced EMF is keep on changing and it periodically changes its direction. After having that this much, okay, half of the time period of the revolution of the coil, rotation of the coil, its direction will be again negative. After this half of this what time period, again it will reverses again in the positive direction. See, after that half of time period, again it reverses its direction in the negative direction, like this. Okay, this is what is happening in the case of AC current. Now if the initial position of the coil is taken to be 0, then normal to the coil, that means theta is equal to the what, 0 degree. Then what happened? Normal to the coil, that means perpendicular. Okay, when the magnetic field and the plane are perpendicular, then theta becomes what? Theta plus pi by 2 or omega t plus pi by 2. So your E will be equal to E naught cosine of omega t, like that. Okay, so we can replace it by your sine function or cosine function, doesn't matter. Okay, in the cosine function, what happen if you instead of starting from 0, if you started from pi by 2 again, then the equation will be like this. As I said, theta, instead of theta, if it is starting from pi by 2 or 90 degree, then what happen? Your initial angle will be pi by 2 plus theta, right? 90 degree plus theta. So then if you replace it this in that previous equation, then E will be equal to E naught cosine of omega t. In that case, what happen if you draw that this sinusoidal function or cosine function, then it will start it from here. Why? Because if you take it t is equal to 0, then omega t will be equal to 0. Cosine of 0 degree is 1, so it will be E naught, it will start from here. Got it? And if you start drawing, then it will, the curve will be like this. Now we started from initial angle 90 degree, right? So if you try to take it to that 0 degree, then you need to move this axis. Okay, this initial y-axis, which will represent for induced EMF, if you shift it backside for 90 degree, then it will come with that of the sine function, same as that in the sine function. It will come like this. If you try to shift this E vector, I mean the y-axis somewhere here, this will be 0 degree. Got it? It comes as a sine function similar to the previous one, like this. Got it? So your sine function and cosine function are almost same. Got it? Both are sinusoidal functions. Got it? Now let's see. So alternating EMF and consequently alternating current can be expressed in sine or cos function. We call it collectively as sinusoidal function. So your sinusoidal function can represent your AC current. Okay, this method of inducing EMF is the basic principle of generator. What type of generator? AC generator. Okay, now let's try to take to that of Eeddy current, which is also known as focal current. Okay, Eeddy means what? It is whirling round. Okay, inside the block of conductor. Got it? Inside the conductor itself, current is whirling around inside the conductor. In the conventional current, the current flows from one end of the conductor to the other end of the conductor. But in this case of eddy current, the current itself is flowing inside the conductor itself, not from one part of the conductor to the another part of the conductor. It is due to what? Due to the change in the magnetic flux inside the conductor itself. That type of current that is produced inside the conductor itself due to the change in the magnetic flux linked with the conductor is called as what? Eddy current or focal current. This has a very great application, many applications. Okay, it can be used in the induction furnace. Okay, or if you want to melt iron or steel so as to make for different material, or if you want to recycle iron, then that iron or steel need to be melted and it need to be cast in the molten state. So in order to do that, what happen, we can melt this iron or steel by using this what induction in the induction furnace. What happened in this case, what happened, that iron which need to be recycled need to be projected, okay, to this changing magnetic field. Then what happened, due to the eddy current set up there, what happened, this will be heated up and it will be melted. Okay, it is used in the speedometer of vehicle, okay, just to measure the instantaneous speed of the vehicle. It can be also used in the dead bit galvanometer. Okay, and now in the galvanometer, when current, okay, is just put off from the galvanometer, then the deflection of the galvanometer will swing. It will not come instantaneously to the zero, rather it will swing to and fro. So just to remove that, we use what eddy current in that coil. Okay, now it is also used in the electric brakes in these bullet trains. Okay, the high speed moving train that cannot be used by any of the brakes, rather it can be used by using what? Changing magnetic changing magnetic field is subjected to the wheel of that iron wheel of that train, and due to that changing what magnetic field, what happened, the induced EMF is developed, and that induced EMF will try to oppose that cause. Cause is what in this case? Motion of that wheel. Okay, so this induced EMF will try to oppose the motion of the wheel, and so it retards. Okay, if it is retards, that means it is brake seems to be applied. Okay, in next, it can be also used in what energy meter or watt meter, you can say, that for consumption of electrical energy in a household, we need to measure how much energy had been consumed by that household by using that what watt meter. Okay, in that energy meter. In diathermy, what happened, eddy current are used for localized heating of a tissue in human bodies. Okay, that also is what using what by means of eddy current. Now self-induction. Self-induction is a phenomenon of inducing EMF in the cell in the coil itself due to the change in the current and hence the change in the magnetic flux in the coil. That means what happened, if there is any change in the what current that is given onto this coil, then what happened, due to that change in the current, there will be change in the EMF developed in the coil itself. Got it? So self-induction is a phenomenon of inducing EMF in the self coil due to the change in the current and hence change in the magnetic flux in the coil. So the changing current in the coil itself will induce what? Induce EMF in the coil itself. That induce what EMF developed in the coil due to the change in the current in the coil itself is known as self-induction. Okay, in the coil itself, if there is a change in current in it, due to the change in current, what happened, induced EMF will be developed in the coil itself. That phenomenon of producing induced EMF in the coil itself due to the change in the current in it. We call it as what? Self-induction. It is not from other coil or other magnetic flux. Okay, the magnetic flux is due to that its own magnetic flux due to change in current in it. Okay, and the EMF induced opposes the growth or decay of the current in the coil, and hence the delays the current to acquire the maximum value. Now what happens when you switch on? Then what happens? Instantaneously current goes to its maximum value or peak value. But whenever that current is allowed to pass through such a coil, just like a solenoid, then what happens? There will be some delay in the growth of the current. Okay, from 0 to maximum, there will be some delay in the time of reaching this maximum or peak value. We call it that as delay in the growth of current. At the time of switch off also, due to the insertion of this solenoid in the solenoid or coil in the circuit, if you try to off the switch at that time also, there will be delay in the decay of what? Current from maximum to 0. If there is no coil, then what happens? Instantaneously when you put off the key, current will go to 0 value, from maximum to 0 value instantaneously during a very short time. But if a solenoid is inserted in the circuit, then what happens? The delay in the decay of the current from maximum to 0 will take some more time. So we call it that as decay of current. Okay, so delay in the decay of current. Yes. Next, self-induction, that phi is directly proportional to the current. Okay, I, that means the magnetic flux is directly proportional to the current. If current is very large, then magnetic flux will be also large, we know it. So your phi is directly proportional to I. So if you want to change this proportionality into equality, then a proportionality constant L will be developed, a constant, proportionality constant, and this proportionality constant is known as self-inductance or coefficient of self-induction of the coil. If current I is equal to 1 unity, then what happens? L will be equal to phi. So from this expression we can define what is meant by self-inductance or coefficient of self-induction. It is defined as what? The magnetic flux linked with the coil when a unit current flows through it. Got it? So your self-inductance is defined as the magnetic flux linked with a coil when a unit current flows through it. Also, E is equal to, we can also define in terms of induced EMF also. So by your Faraday's second law, your induced EMF E is equal to minus d phi by dt, right? Rate of change of magnetic flux. Or if you take it that one, E is equal to minus L di by dt. If you try to differentiate it this, then it will be what? D phi by dt will be equal to what? L di by dt, right? So if you take that L outside, then E will be equal to minus L di by dt. So if you take it that if di by dt, that means rate of change of current, okay, is equal to 1, then what happen? Your L will be equal to E if you take it only the magnitude, okay. So if you take it this di by dt as 1 unity, then what happen? Your L will be equal to E. So your coefficient of self-induction or self-inductance may also be defined as the induced EMF set up in the coil through which the rate of change of current is unity. Got it? It is defined from this expression taking this condition. Got it? So self-inductance is defined as the induced EMF set up in the coil through which the rate of change of current is what? Unity. Got it? Similarly, we can also find out for coefficient of what? Mutual induction also, that will come later on. So SI unit of self-inductance is what? Henry. Self-inductance is said to be 1 Henry when 1 ampere current in a coil links magnetic flux of 1 Weber. Got it? It is very easy and it comes from that definition, from that expression only. We are not saying that expression says only, okay. So self-inductance of a solenoid, what happened? you take it as solenoid, okay, of whose length is denoted by L. Current I is flowing through it and its cross-sectional area is A. And let's take it that the total number of turns of such solenoid, let's take it this as capital N. Got it? Where small n is nothing but this is a number of turns per unit length. In a unit length, how many turns are there? That is denoted by what? Number of turns per unit length denoted by small n. We know that the expression of what magnetic field due to the solenoid is given by B is equal to mu naught Ni, right? Where mu naught is the permeability, absolute permeability of free space, right? N is the number of turns per unit length. I is the current flowing through the solenoid. Then what happened? In each turn, okay, in each turn or in one turn, you can say the magnetic flux link will be equal to what? BA only. If there are small 5 turns, there will be 5 times of BA. If there are 3 turns, it will be 3 times of BA. So this is the magnetic flux link with one turn of the coil, okay. This B will be equal to mu naught IA. If you replace it all those things, then what happened? Your magnetic flux will be equal to what? B is equal to mu naught NIA by L. From where it is coming, we know that your small n is nothing but this is a total number of turns per unit length, right? So if you want to express this n, then it will be equal to what? N by L. Instead of n small n, you need to replace it by capital N by L. Here, this is small l, that means this one, length of the solenoid, and this is capital I. Okay, I means the current flowing to the solenoid. So magnetic flux link across n turns of the coil is what? This capital N is the total number of turns. So if you want to express it in terms of total number of turns, then what happen? It will be equal to what? Mu naught N square I A by L. But 5 we know that it is equal to Li. So if you replace it here, then I will cancel and it will be what? Mu naught N square A by L, right? Will be equal to what? If you come to that of that number of turns per unit length, then it will be what? N square A I. Got it? Then what happened? It will be equal to, this is not I, actually this is N small n, I'm sorry. So this is will be what? I will be cancelled. If you equate it here, I will be cancelled and this will be small l, okay. If you use it, this N square, okay, N means number of turns per unit length, so 1L and 1L will be cancelled in the numerator, so 1L is still there, so it will be mu naught N square A into L like this, okay. It is also seen here. And the energy in the inductor, we can find it out like this. The small amount of work done in establishing a current I, okay, in a time dt, it will be equal to what? dW will be equal to what? Minus EI dt. Got it? EI dt. So what happened? This will be the amount of small work done in transferring that much amount of current during this small time dt. So if you want to find out, then what happened? Instead of E, you can replace it by that of what? L di. Got it? Since E is equal to minus L di by dt, somewhere in the previous one we have used it, this one. So by using that, E will be equal to L di by dt, and if you put it there, then minus will be also with this minus plus, and it will be coming out as Li di. So if you want to find out for total work done, then we need to integrate this W, so that it will be equal to what? Integration W will be equal to integration of dW, and it will be equal to what? Integration of Li di from 0 to I naught, minimum value to maximum value, and it comes out to be what? Half Li naught square. You know how it is integrating? L is a constant, okay. As long as you are not changing this inductance, L will be remaining constant. So you keep that outside the integration, and we know that integration of x to the power n, integration of x to the power n dx. this will be equal to x to the power n plus 1 divided by n plus 1, right? So our x is here in this case is I, and instead of n we are having the power as 1, so we will have what? Integration of I di will be what? I square 1 plus 1, it was 1 here, so 1 plus 1 will be 2 divided by 1 plus 1 will be 2 here, like this. So I square by 2 will be coming out. Got it? And if you replace it, this variable I by the upper limit I naught, okay, then you will get it this. In the next term it will be what? If you replace it by the lower limit 0 here, then 0 square will be 0, 0 divided by 2 will be again 0, so no need of putting that one. So the total work done, okay, which will be stored in the form of electric energy, in the form of magnetic energy rather, it will be equal to this. W is equal to what? Half Li naught square. Got it? Yes. Mutual induction. Mutual induction, mutual means what? One will be happening and the effect will be felt on another coil. So mutual induction is a phenomenon of inducing EMF in the secondary coil due to the change in the current in the primary coil, and hence the change in the magnetic flux in the secondary coil. Got it? So what happened? Changing in current takes place in one coil and the induced EMF is happening in another coil. That phenomenon we call it as mutual. Got it? So what happened? That change in the magnetic flux, I mean the magnetic flux that is felt by the secondary coil, let's say, due to the current I1 flowing in the primary coil. So your phi 21 is what? This is a magnetic flux. Your phi 21, this means this is a magnetic flux, okay, linked in the secondary coil, second coil, due to the current in the first coil. Okay, phi 21 means that one. So your phi 21 is directly proportional to which current? Current I1 that is flowing in the first coil. Okay, or phi 21, if you want to change it from proportionality to equality, then one constant again, m, is required. This m is nothing, it is the constant of proportionality known as mutual inductance or coefficient of mutual inductance. Okay, similar to that of self-induction, you can also define it mutual inductance. Okay, if I is equal to 1, then m will be equal to phi 21. Okay, so what? Your mutual inductance is defined as the coefficient of magnetic flux linked with the secondary coil, okay, when unit current flows through the primary coil. Got it? This current is flowing through the primary coil and the magnetic flux is felt in the secondary coil. So your coefficient of mutual induction or mutual inductance may be defined as the magnetic flux linked with the secondary coil when a unit current flows through the primary coil. Same as that in terms of rate of change of current, you can also define it. Your E2, that means induced EMF in the developed in the secondary coil, will be equal to what? Minus d phi 2 by d phi 21 by dt. That means rate of change of magnetic flux in the secondary coil due to the current in the primary coil. Okay, so or E2 will be equal to what? Minus m di 1 by dt. So if this rate of change of current in the secondary coil is met unity, then your mutual induction, that is what fell in the secondary coil, will be equal to the induced EMF developed in it. So your mutual inductance is defined as the induced EMF set up in the secondary coil when the rate of change of current in the primary coil is what? Unity. Got it? Unit is same SI unit of mutual inductance because this is inductance. Okay, whether it may be self or mutual, it is inductance. So its SI unit will be Henry. So mutual inductance is said to be 1 Henry. Okay, you can define 1 Henry in terms of that self inductance or mutual inductance. Okay, so mutual inductance is said to be 1 Henry when 1 ampere current in the primary coil links magnetic flux of 1 Weber across the secondary coil. Okay, or you can also define, this is for the first one. Okay, for the second one like this, mutual inductance is said to be 1 Henry when a unit rate of current, okay, rather 1 ampere per second in primary coil induces EMF of 1 volt in the secondary coil, then that type of mutual inductance is said to be what? 1 Henry. Got it? Now mutual inductance of two coaxial solenoid. Now whenever one current is flowing, okay, whenever one current is flowing in one coil, and if you try to find out the mutual induction in the another coil, okay, same will be having the effect when the current is flowing in that another coil, and if the mutual inductance is felt in the one coil. Okay, now when magnetic field due to the primary coil is what we know, that due to the solenoid it will be B will be equal to mu naught Ni, right, where N is the number of turns per unit length, I is the current flowing through it, and mu naught is the absolute permeability in free space, right? So your magnetic flux, this is a magnetic field due to the primary coil S1. Okay, primary coil is this blue one, secondary is this brown one. Okay, so what happened, current I1 is flowing in the primary coil, got it. The magnetic field that is produced in the primary coil will be what, B1 will be equal to mu naught N1 I1. The magnetic flux link across one turn of the secondary coil is what, this is only for one turn. Okay, we are not talking of that of total number of turns. So for that one turn, what happened, you will have B1A, where B1 is the magnetic field induction produced by the primary coil. Okay, and this flux is what, through each turn of that secondary coil. Okay, so your secondary coil will be B1A, and B1 will be equal to what, mu naught N1I. So you replace it here, and if you know the total number of turns in the primary coil N1, then you can replace it this small n by N1 divided by L. Got it? Total number of turns divided by total length. You will get it that number of turns per unit length N1, right? So you can use it this way. So it will be mu naught N1 I1A divided by length of the solenoid. Got it? Now magnetic flux link across n turn of the solenoid. This is for a single turn. Okay, and if there are total number of turns in the secondary coil, suppose capital N2 is the number of turns. Okay, total, this one N2 is the total number of turns in the secondary coil, N1 is the total number of turns in the secondary coil, primary coil. Then what happened, you need to multiply it by N2 here. Why? Because this is only the magnetic flux link in one turn of the secondary coil, and if you want to find out total magnetic flux link with the secondary coil due to the current I1 flowing in the primary coil, then you need to multiply it by how many turns you are having in the secondary coil, because secondary coil is going to feel that magnetic flux. Okay, so N2, so here you multiply it simply by N2 and you will get it that 521. But we know that 521, that means magnetic flux, okay, in the secondary coil due to the current in the primary, okay, I1, this will be equal to M21 by I1. So this is a mutual inductance of the secondary coil when current I1 is flowing. So this is the expression of the mutual induction, the magnetic flux I mean. Then what happened, this 521 are same. So if you cancel this, if you after equating, if you cancel it, this I1 and I1, then M21 will be equal to what, mu naught N1 N2 A by L, right? If you want to express it in terms of that of number of turns per unit length again, then it will be mu naught N1 small n2 A into L, right? So this is the what, coefficient of mutual inductance or mutual coefficient of mutual induction or mutual inductance of the secondary coil when current is flowing in the primary coil. Now in the next case, you can also do it in a very similar way, that current is flowing in this secondary coil, and if you try to find out the mutual induction of this primary coil when current is flowing in the secondary coil, the same thing it will be happening here. So this is the mutual induction of, okay, mutual induction of the coil what, primary, due to the current I2 flowing in the secondary coil. You will have the same expression. So what happened, we can conclude from here that whether current is flowing in one coil and mutual induction is felt in another coil, same is happening if you interchange the current also. Okay, That is what it is having. So for two long coaxial solenoid of same length and cross-sectional area, the mutual inductance is same and leads to the principle of reciprocity. When one is current is flowing here and mutual inductance is felt in another coil, or when current is flowing in that coil and mutual inductance is felt on the other coil, it gives the same value. So your mutual inductance, whether current is flowing in one coil or the other coil, mutual inductance will have the same value. So these are some additional informations that we have come across at the end. Okay, if two solenoids are wound in a magnetic core of relative permeability mu r, then instead of mu naught you have to replace it by mu r. Okay, this will be mu naught mu r times n1 n2 a by l. Just you multiply it by mu r, that much. Okay, in that previous expression. If the solenoids S1 and S2 have number of turns N1 and N2, total number of turns N1 and N2 of different radii R1 and R2, where R1 is less, where R2 is large, then what happens? Mu, this one M will be equal to, mutual inductance will be equal to mu naught mu R N1 N2, and then you need to take the cross-sectional area of that smaller solenoid of whose radius is small by L. Got it? Mutual inductance depends also on the relative placement of the solenoid, whether those two solenoids are coaxial or whether it is perpendicular or whether it is far away from it. Okay, it depends on it also, and that is what we call as coupling. Okay, coefficient of coupling K between two coils having self-inductance N1 and N2 and mutual inductance M is what? K will be equal to M divided by root over of L1 L2, where L1 and L2 are the self-inductance of those two individual solenoids. Generally K is less than 1. Okay, this K is less than 1. What is this K? This is coefficient of coupling, we call it. Okay, if L1 and L2 are in series, if the two solenoids are kept in series, then your self-inductance will be equal to what? It will be equal to the sum of the individual inductance of those two solenoids. It is similar to that of finding of equivalent resistance in the case of resistors. When they are in series, the equivalent resistance is given by the sum of the individual resistance, like this also. So your equivalent self-inductance will be equal to what? Sum of the individual inductance, self-inductance I mean. If L1 and L2 are in parallel, then same thing in the case of parallel. So reciprocal of the equivalent inductance, self-inductance will be equal to sum of the reciprocals of the individual self-inductance. So that's all for it. Okay, for today. I think from here you will know all about this electromagnetic induction up to what your mutual inductance. Okay, the other remaining things we will try to see in the next video.